All right. Yeah, I always start. I noticed that all my slides start with all right. So welcome to our class number 7 about hidden Markov models, and then the variable Markov oracle, which is an extension of some of the string matching algorithms to deal with audio or features. So first of all, what is the hidden Markov model? The idea of a Markov chain that we have seen before kind of corresponds to being able to switch between states in some sort of a finite automata. And then we actually see the operations. They're kind of one-to-one related to the alphabet that makes the transitions. The idea in hidden Markov model that we kind of create this one step beyond the Markov model by hiding it. So this is where the hidden comes from. And what I mean by hiding it, we still have a Markov chain structure that does not necessarily correspond to actual emissions or actual symbols that we see, but it actually represents a probability distribution over some alphabet. So I will in a second give an example of this graph, but graphically this representation contains all the elements of a hidden Markov model. Hidden in the sense that we observe a sequence. So these O's will be the observations. And the typical use of Markov models is for time domain signals. So we get these O's, 1, 2, 3, 4, 5, and so on. This is our time index. But each O can be generated by some hidden state. So the states are the probability distributions. So here already we introduced the concept that we have some kind of an underlying hidden random process that moves between distributions. So the B1, B2, B3 are a probability distribution over the observations. So we have a finite alphabet, and in each state we actually switch distributions. Okay. Now the switching process is done using the Markov method, or the math is transitioning from one state to another one. We can also move back, we can return to the state. Normally in speech, we have these left to right Markov chains. So we kind of proceed, either stay in a state or move to the next one. Sometimes we can skip a state. But as a general formulation, it's even more general than what's written here. It basically like an automata here that moves between states. And every state then it becomes kind of an information source of its own. It's a probability distribution, and then you have to sample it or bang it with some random trigger, and it will output one of the possible elements from this distribution. So in some sense, the O1 and O2 and O3 are independent, but the overall process that switches between these distributions has a time structure. So it might be a little confusing in such an abstract way, but just one more sentence about the terminology. When we have the observations, we also try to find which state generated the observations. So we have a state sequence, which is part of the task, as we will see in the hidden Markov model, to estimate or find the best explanation or the maximum likelihood solution that will give you the sequence, the most likely sequence of transitions between these states, considering also their output probabilities, so that we would find the most likely explanation for how this sequence was generated. So what does that mean? This is a much simpler example, a classical example of hidden Markov model, and I think it will make much more sense. So assume we have 3 urns, each one containing these colored balls, whatever, green, yellow, red, and blue, but in different proportions. So, as a multinomial distribution or any kind of probability that you want to consider here, you pick up a ball and I won't go into questions. Are you returning the ball to the urn or not after you sample? Let's assume that you do. You just kind of take this ball and you can keep sampling. You're drawing balls from the same distribution, or you can switch. So what you see, there's like a screen here between the urns and the sequence that you lay out here. And the observer or whoever looks at the outcome of this process only sees these balls. He doesn't see the hand that moves between these urns, so he doesn't know from which urn the ball was drawn. Now, do we have any chance to estimate which urns were picked up? Well, of course, if they have the same distribution, it would be equal. It wouldn't matter, but assume that one of the urns is more likely to have, let's say, green balls, and another one will have more yellow, and one will have more red balls, or the proportions are slightly different. So by seeing an observation, we are kind of more likely maybe to say that probably the yellow came from the urn that had more yellow balls, but there's also this underlying transition process. So we probably don't want to always jump and say, well, if this urn had most yellow balls, so if we were here, and then green had here, so we'll jump here and here and here. There is some probability that you actually stay and you switch. So this is kind of the combined problem setting. We have this set of, the definition, this set of mathematical definitions that represent the hidden Markov model. You have values for the hidden states, or are the states. In this case, we have 3. You have the values for the observations. So these are the M balls. The N is 3, and M here will be 4 because we have 4 colors. You have some initial probability where you would start this process. You have transition probabilities between the urns, and you have the observation probability. If you are in urn number I, what is the probability to generate ball number K? Okay, so given this setting, which is also represented here as these 3 different urns, and the transition probabilities. So this graph is a little bit more of a complete Markov chain over the hidden states. And again, they're hidden because you don't know, nobody tells you which urn you're looking at. All you see are the balls eventually that you drew from these urns. So the Markov process is hidden, and the HMM method is kind of a description of this problem setting, but also it's an algorithm that will allow us to learn the model given the observations. So the 3 typical problems that the HMM addresses are as follows. One is, assuming that you already know the model, you know the transition probabilities, you know the distributions, okay? And let's say you have several models like this, okay? Or even, sorry, let's assume you have just one model, okay? Given one setting like this, and I give you a sequence, okay? You can kind of go through the process of estimating for each state where it was and moving to the next step. So this would be your full kind of unrolling the process. So for the sequence of states that you see, if you had red states and then green states and blue states, each one of the urns will give you some probability of seeing the red, let's say, and then given that state, there is some probability that you'll move to the next state or stay in the same one. So for every sample, you kind of construct this graph. You basically unroll this Markov model into a sequence of observations. And the numbers here, the transition probabilities, there are probabilities of emission here. You get some kind of a graph that all possible transitions are possible, are valid here. But you can think about this whole problem is finding the least cost or the most probable transition. So given a sequence, okay, you can actually go and find the trellis, this kind of the name of this type of representation, that gives you the most likely or the most probable sequence. So let's say here, it will be maybe one of these sequences. Now, by observing this, you actually have to decide what is the sequence of states. This problem is called segmentation, okay? But it kind of happens as you go and try to find, your most probable path. And when you sum everything together, you also have an overall probability, okay? The likelihood of a sequence of observations. So if you have such a sequence that is generated here, by finding the most likely path, you will also have eventually a number, the total probability that this sequence was generated. So given an existing model, we immediately have these two results. One is given a sequence, we have the likelihood of that sequence. And as part of the process, we also find or segment this sequence, or we annotate this sequence as a sequence of these hidden states. So given a sequence of observation, we find the most likely sequence of hidden states. Now, let me go back for a second to the classification issue. Where is the classification? This is just a likelihood. Well, if you have now multiple models like this, because let's say this model represents some sort of a acoustic unit, okay, or some quick sequence of events in music or audio, okay, and then you have another model with different emission probabilities, different transition probabilities that describes another segment of audio. It could be, kind of a phonetic transcription of a word, or you can think about some sort of a sound event. So if you think about different sound events represented as models, given the fact that you can input a sequence into a model and get the likelihood, now you have the classical or the canonical classification problem. Now, since machine learning is kind of statistics, but with a very specific application to, let's say, classification, decision making, and for our purposes, of course, it's generative modeling. But the classification part is usually the idea that if you have different models or different labels, so let's say each model like this will have its own label, and you run your observations through different models like this, you will take the maximum likelihood solution. So this is one way to classify by using HMM, because if you have multiple HMMs trained on different classes of sounds, the most likely sequence, or the HMM that gives you the highest likelihood of generating this sequence, will be the one that we will basically assign or consider as the source of that sequence. So kind of that conceptual approach, I just want to say it once again. So if you have multiple probabilistic models, and you and each probabilistic model basically gives you some distribution over the probabilities of things that you observe. So given out the observations, you can plug this into each one of these probabilities, so probabilistic models, and we would kind of assume that's kind of the convention, or it's also very logical, but you need to understand that there is some kind of conceptual convention here, that we would say that a sequence was generated by source A or model A versus model B if source A was more likely, it has a higher probability of generating that sequence. So this is kind of the underlying classification thing. If you have multiple models trained and you now have a new sequence, you will estimate the probability, and you will classify that sequence as belonging to the model that where that sequence was most likely, or the model that most likely generated that sequence. And really the power of the model comes from the last one, which is the learning. And the idea is that you can either fix a topology or maybe do some other kind of a little bit less confining considerations. But let's say if you assume that there is some kind of underlying hidden structure, and now you have a lot of observations, you can run so-called expectation maximization or Baum-Welch algorithm, and these names mean something only to people who already have been exposed to machine learning classes. We'll mention expectation maximization because that's kind of a general principle also when we talk about neural networks next week. So I bring this as a concept, but regardless of the algorithm that allows this, the tool or the third task and the EM as a tool that allows to accomplish this task is that given observations, you can actually train models, which means just given these sequences, you can eventually create the model that will give you all these parameters. It will give you the transition probabilities, the observation probabilities, and the initial state probabilities. You might, this is something you might assume, but I mean, once you're given, once you define your hidden states, your observations, you can basically derive everything else just from the data. And again, this is generative model really, because this is a process of this process, more explicitly, they are descriptions of how the data was generated, and you estimate these generative models. So how it's used in speech. One of the most powerful applications of HMMs is for speech recognition or text-to-speech, but we'll also see the generative aspect in a second. So given a set of, or if you train the model now, or you use this to train, eventually this is the correspondence. We think about the speech waveform as something that was first of all segmented into speech vectors or features, okay? And this is where our different ways of representing speech are useful. You can think about these as FFTs, you can think about them as some MEL spectrum or MEL capstrom. We mentioned MEL capstrom, we didn't really explain what they are. Or you can think about them even as representations of like a linear prediction with filter coefficients and maybe pitch. But once you analyze, you do some sort of an analysis of your data, now you have a sequence of these vectors, speech vectors, and you assume that subsequent vectors were generated, let's say, by the same phoneme, the same vowel, and the speech changes. So the model changed, right? So if these are filters with different formats, this will be maybe corresponding to one format, and then it moves to another one, and the third one maybe also the pitch moves and changes. If our task, okay, if all that we care about is the sequence of, let's say, transcriptions or understanding what this means, we actually want to say all of these maybe were assigned to one state. If this is, let's say, the phonetic transcription, and then this segment was some other phonetic state, and these two were generated by another one. So you can kind of see that this process of finding the hidden states could mean something like transcription from audio. And the transcriber is actually this hidden Markov model. Now, each phoneme, okay, basically becomes some probability, right? We spoke about the emission probabilities. So each state here has these emission probabilities. Very often we use something called Gaussian mixture model. I just bring this as an acronym here, but the classical HMM for speech, or the continuous HMM or HMM with continuous features would be Gaussian mixture model over some distributions of feature vectors with a discrete hidden Markov model that moves between the states, okay? In musical applications of HMM, one typical example is using HMMs, or training HMMs to detect chords. So the way it is done here, you can think about this as um, you know, some pre-processing. So these are the chromograms, and we mentioned chromograms. So there is quite a lot of processing that was done before. And if we derive these 12 classes, now we want to estimate from the distributions of these vectors the underlying hidden states, which are the chords. And I think conceptually it's also kind of revealing or interesting to realize that concepts like chords in music in some sense are hidden representations, unless you really have a lead sheet where the chords are spelled out and written. But many times when you play music, you do not know what the chords are. Maybe the composer had them in mind when he composed. If he uses like a so-called chord first composition method, we can lay out your harmonic progression and then you write the notes. Maybe he was writing really polyphonic music and the kind of the harmony emerge from the different voices. But if your task is given an audio to find the chord transitions, our evidence or our observations are these noisy vectors. Now, you can see here that in some cases, I mean, these vectors are quite, there's quite a lot of variability. They're quite noisy. So the question is, are we going to estimate a different chord? Well, most likely we'd say, there is a chord of E, or maybe because it's E and G and C, this is a chord of a C. But I mean, in some cases, you have here a very strong E, and we don't have really strong C and G. So for those who know musical harmony, why not jump to a chord on E, right? So do we estimate everything here as C chord that has the, triad C, E, G? And then every step we jump, so here we'll be basically jumping to the strongest one, G, and coming back to E. Or we want to kind of smooth them out and say these are all kind of noisy versions of a C chord, C major chord. And then we have this underlying transition between the chords. So the segmentation issue here is quite evident. What we want is to smooth out these decisions so that we maybe collect enough evidence to decide that we actually jump from chord to chord here. And can look up the original paper and need to make sure that I put it in the repository if and just to facilitate finding it. But what this shows you, this is the true and this is the recognition. And we have to define, of course, our state space. So this work estimates only a major, minor, and diminished chords. So because we have 12 notes times 3, we have 36 states. And you can see that the true transcription or the true chord sequence was C major, D minor 7, C dominant 7, C major, A minor, and so on. Sorry. And this is the hidden states that the HMM found. Oh, okay, sorry, I have to notice my battery is going low. All right. So if these are so this is the ground truth, and these are the recognitions, and you see most of the time it actually falls correctly up to one frame, left or right. This doesn't have any prior on the beat or something kind of to tell you that you actually are more likely to make transitions on beats. And of course, the categories are way smaller than the original one because it doesn't know how to recognize diminished 7, just tells you diminished, or dominant 7s, and it just says it's G major basically. So put this for a second. So the transition matrix is 36 by 36. You can think about this transition matrix as that Pij that we have seen when we were talking about Markov models. This first order transition matrix between all the states, and kind of encodes to the first order the rules of harmony. But again, this is hidden. So this is learned from data. And once you're in a specific state, like a C major chord, it gives you distribution over the chroma. So again, this is the Aij, the transition probabilities, and this is B of O, where O's are the chroma, the 12 values, and the B corresponds to C major chord. So these are the two elements. And this is the trellis, basically how we enroll it and how we do the transcription. So I think it kind of gives a very clear model or statistical interpretation, statistical model for the chord estimation problem. One kind of a little bit more elaborate example of hidden Markov models for music, where the task is actually to work on symbolic music. And why would we need a hidden Markov model for MIDI or for symbolic music? So we kind of already hinted at this problem when we spoke about how we would, say, use Lempel-Zeev for polyphonic music. Because we have multiple simultaneous notes, if you think about the cross alphabet or all possible combinations or occurrences of notes, and later on we'll talk about the idea of one-hot encoding. So if you want to say you are in a specific state, and that state corresponds to all possible simultaneous occurrences of notes as you go through a musical piece, your alphabet is huge. Right, so even if you allow only 4 notes or 5 notes, or not talking about 10 notes, if you think about piano, well, let's take 10 because you have 10 fingers. So if you could play up to 10 notes together, and let's say you just use 2 octaves, 24 notes, you can, I'll let you figure out how many combinations of possible chords we have. And this will be, if we want to actually give a label to each possible occurrence of these combinations, and that alphabet becomes huge. And with such a huge alphabet, we won't be able really to see any relations between things that sound kind of the same, but maybe have different voicings. So we do need to condense. We need to have a compressed representation. And I also kind of try to connect this to the idea of rate distortion, in the sense that by going from the surface, from the observations, from the visible observations to the hidden states, that hidden representation is lossy because you don't really know how to recover the original data. But I mean, it can serve a lot of purposes, and one is maybe you can recreate data with an error, or maybe you, you know, if the question that you want to deal with is analysis, like segmentation of music, transcription, then we actually care about the hidden states. But if you want to generate, and this is why I brought this example, it's now trying to use HMM generated back. The generation will be kind of a, I don't want to say funky or flaky or whatever the word will be, but it won't be really the true music. We still have this very rough approximation of music by encoding this into hidden states, and then from every hidden state, kind of randomly selecting notes. But you know, you have a link here to more examples and also the implementation of this model. And for some reason, HMMs for music didn't capture a lot of attention. And not so much because of the quality, maybe because it takes a while to build and train models, and once you have very complicated models today with neural networks, and it's not clear if there is an advantage. And the other difficulty is that they all need to be trained, so it's hard to run an HMM live, like I was showing in the previous machine improvisation things, where you can train this on the fly. So again, it uses this EM Baum-Welsh for training, and the work by Anna Yanchenko describes several architectures. It has left to right, which I kind of mentioned before. It has a higher order factorial HMM, so there is a variety of, there is a small kind of HMM zoo here that each one gives slightly different results. Let me play this, the generative part, you know, the pieces sampled from the model. And yeah, I think we'll, yep, sorry. And then we'll move on to the next one. It should work, right? Yeah. Just work. Yeah, we have the audio. Okay, yeah. Wanted to check that we have audio. We had audio. Yeah, I'll make sure also that we have the slides with the links available. So you could hear that there are these kind of slow moving chords because it was trained on a prelude by Chopin, which is kind of the funeral march. So it kind of slowly picks up on the structure, gets the chords, some melodies, but it's far from being the original composition. But kind of proves the concept that you can actually so if you recognize the piece, you might kind of enjoy more kind of comparing the original to that composition. There are many more examples. Yeah, so I think this was my kind of brief introduction to hidden Markov models. I'll stop the recording and answer some questions.